Hi, this is Dr. S.P. Asaf from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, now we are going to start the last module, which is absolutely based on the vibration measurement techniques. In that, you see here, first we would like to discuss about the basics of that how we can measure the dynamic parameters, what are the instruments particular which should be there to measure those basic dynamic parameters, and what exactly the nature of these the vibration features are basically. Till now you see here we mainly discussed about the vibrations, the causes of the vibrations and the sound together, how we can reduce the vibration you see here at the source or at the receiver end or during the transmission path. Then we adopted the two main we can say techniques. One is the isolation, means when the isolators or the absorbers are there, we can say these are the passive vibration control devices. And the second, which we discussed about, the active vibration control, in which we mainly discussed about the sensor and the actuator feature. At the same time we discussed about the materials, the smart materials through which we can reduce the vibration either by just putting some adding some kind of damping, or just by creating some kind of the actuated force exactly opposite to the vibrating excitation forces. Then we solved some of the numerical problems, that how we can adopt those devices through which we can control the vibration excitations. So now you see here in this lecture we are going to discuss about the basics of the vibration measurement techniques. So if we talk about the vibration, then we know that it is nothing but the like the back and forth or some kind of repetitive motions of an object from the point of rest or some the mean position. And when we are talking about the friction free systems, we know that the mass would continuously will oscillate or move without having any kind of obstructions. But when we are talking about the real systems, we know that there are damping through which you see here the vibration is gradually die out, and the rest positions are coming even after several cycles of the motion. Even you see we can say that whatever the system inherent natures are. But if we are acting any external excitation force, then certainly you see here it will add some kind of more energy in the excitation features and we will have more vibrations. That is what the basic nature of the vibration is. So if we want to characterize the vibratory motion, then we know that we can only characterize using the period of vibration, or in other terms we can say the frequency, that what exactly you see then the frequency features are there, whether the system is exciting at the low frequency or high frequency. Just like you see we discussed about the human vibration, and we know that this is absolutely starting from 0.5 hertz where the motion sickness is there to at the most you see 80 to 100 hertz, where we know that the discomfort level right from you see the heart, or we can say our brain, or whatever the muscles are there right from the leg or at the hand part, you see they are all you see they have their own natural frequencies for that. So the discomfort can be created at the low frequency, and even the high frequency excitations, like you see the machines are there, whether the spindle is rotating or any the bearing or the gears are being under the rotating features, the excitation frequencies are almost in terms of the thousands hertz, means in terms of the kilohertz rather we can say. So this is one way to characterize the vibration. Second is the amplitude. The amplitude means you see here whether the displacement or velocity or acceleration, these are the three parameters through which of their amplitude is here, through which we can describe the real characteristic of the vibrations. And the last is the phase. When we are trying to relate those things, we know that not only the time derivative features are there, but even if we have the harmonic or any kind of you see the motion, then the phase differences are also being there with that. So from frequency, amplitude, phase or period, you see through with the using of these key concept, we can characterize the vibratory motion. The continued vibration of the spring mass system would then you see we then have the repetition features in the characteristic part using the various cycles. And all the machines which are producing vibrations are simply the functions of these machine dynamic parameters. And when we are talking about the machine dynamics, we know that the key features are the alignment and the balancing of these rotating masses. Because the measuring of the amplitude of vibration at certain frequencies are simply providing the valuable information about the accuracy of shaft alignment, and also you see the balancing condition of these, we can say, the rotating masses like the bearings, like gears, or we can say the effect of this machine due to resonance from housing, piping and other structures. And when these devices are under exciting forces, we know that a clear exciting frequencies are being coming out through the transmission features of the machine, and we can measure and we can characterize rather the kind of excitations from that. So, vibration measurement is an effective non-intrusive method to monitor the machine condition during startups when the transient feature of the vibrations are there, during shutdown and during normal operations. So, we know that when the startup and shutdowns are there, this is one of the important part that you see that how we can measure the transient form of the vibrations, and when the steady state feature is there under normal operations, how we can monitor the machine health using measurement of vibration. Because when we are saying that the machine is under running operation, that means the dynamic feature of the machines are there, that means there is a motion feature in the machine, and when there is a motion in the machine, one of the best technique to identify the fault or to locate the fault at any specific part of the machine or the machine itself, the health condition, the vibration is the significant, we can say, like vibration signature is the significant part to do this. So, vibration analysis is used primarily on the rotating equipment, right from you see, like we can say the steam and gas turbines, pumps, rotors, compressors, the paper machines, rolling mills, machine tools, gearbox, right from small machine to the heavier machines for even power production of more than 1000 megawatt by a single unit, like you see the supercritical boilers and supercritical thermal power plants are there, where a single unit can generate more than you see 900 megawatt. And then we can assume that what the huge rotors are there and what kind of you see the thrust and like the journal bearings are there, at which the huge kind of exciting forces are being generated, and we have the huge amount of vibrations, or we can say like the sounds are there. So, vibration analysis is used to determine the operating and the mechanical conditions of the equipment. So, major advantage in that you see the vibration analysis can simply identify the developing problems before they become too serious and cause the unscheduled downtime of the entire system. And simply like we are achieving this by conducting regular monitoring. We are saying that the periodic maintenance feature, we are always trying to measure the level of vibration and the exciting frequencies, that what kind of you see the dedicated exciting frequencies are there in the spectrum, and what is the vibration amplitude associated with these like the dedicated frequency. We could easily figure out that these mechanical vibration, either we are doing the continuous basis, means the online fault diagnosis, or on the periodic maintenance feature, it is clearly indicating the health of system. So, regular vibration monitoring can detect deterioration or any defective part in the various rotating components, right from the bearings, the mechanical looseness, or even the worn or any broken gears, or the shaft, whether it is a line shaft, any kind of misalignment is there, unbalanced features are there, or various other rotating features or component through which you see these excitations are being coming there itself. So, vibration analysis can also detect, as I told you, the misalignment and unbalance, which are nothing but you see here, it is a clear deterioration of bearing or the shaft part. So, trending vibration levels can identify the poor maintenance practices, such like you see we can say the improper bearing installation or replacement, improper lubrication adopted, so that you see here the wear and tear is more, inaccurate shaft alignment, even improper, we can say imprecise rotor balancing, and you see here the gear macing part means like the axial axial features of the gear mounted shaft. Then there is a meshing part and there is a huge impact forces are being created or generated at the meshing of these gear part. Or even when the gears are being mating, what is the lubrication features which are not being appropriate, and at that time you see whatever the fill thickness which are being generated is not able to or is not sufficient to take the energy back, and we have the use kind of vibrations at that point. So these are the possible like causes, and that is why you see the vibration measurement is one of the important part prior to go for the control adoptions. So that is why this part is more important than even in like adopting the vibration the control technology or like this method, that we should first try to feature out that what exactly the vibration part is. So when we are just going for the basic characteristic of vibration, we know that you see first of all we need to check it out through this sensor, that you see how we can measure accurately the vibration and what exactly the characteristics are there. So modern vibration monitoring has its genesis in the like we can say in mid 50s with the development and application of basic vibration sensors, which is the heart of the modern computerized fault monitoring or condition monitoring or health monitoring system of the machine. So we can say that if you are just going with the basic fundamentals of the vibration monitoring in any of the rotating machine, we know that these are simply providing a warning of a gradual approach or suddenly we can say encountered excessively high vibration level. This is nothing but you see like the high vibration level means whatever the oscillatory feature of these the mass is, if it becomes more and creating you see like more kind of you see the frequency part, or we can say more kind of you see the sound generation is being created, that means you see here somewhere there is some problem, because of that this huge amount of you see the exciting energy or exciting forces are being generated. So that can be straightway monitored out, and that could be potentially damage of the entire machinery itself. So if you see this diagram, it is clearly saying that the vibration amplitude, this is showing in terms of acceleration when you see the masses are being under like the motional feature, and you see the the acceleration part is coming, then you see the vibration acceleration with the time when the machine is like just producing the vibration acceleration of this level, we can say this is what the comfort level, no problems are there, because when the machine is in the rotating part or translating part or any kind of motion, certainly due to the inertia forces we have these like we can say the varying compliance feature of this vibration, the self excited vibrations we can say that. But when the things are being like just increasing, that means there is some like the additional features due to misalignment, unbalance, or due to various other reasons, the defective part in the bearing, gears, or the like we can say the shaft. Due to that, this like the vibration is continuously increasing. That means you see the exciting forces are quite dominating as the normal forces. So you see here we can put the alarming situation just based on the transmission, and you see here whether this vibration like this amplitude or the energy at that point you see here is now damaging the other we can say whatever the component. So this is what the alarming situation, and once it is being like approached up to that point, it can be tripped there. So the entire machine is now at the shutdown. So there is you see we can again recheck that which part is inducing this vibration or which part is creating you see this huge sound, we can straightway treat or cure that. Or else the second phase is when you see like these are being operating, and you see over the time it is not showing any indication that you see that sudden vibration, this vibration is increasing, but due to some fault or due to some like fault may be of any nature, maybe some defects, maybe some you see like these aligned problem, unbalanced problem, anything you see here at the rotating component, there is a sudden increase, and this sudden increase is creating huge amount of we can say like the force is there itself or the exciting energy, which shoots be like when it is just approaching up to alarming level, we need to strip the part. So vibration is one of the best indicator for these machines where the like the motion or rotating, reciprocating, anything is one of the key part for any processing like the machine itself. So it is a good indicator for identify the health of the entire machine itself. So trending the machine vibration level over an extended period of time can potentially provide the early warning of the impending excessive vibration level on the other problems, and thus provide plant operator with the valuable information for critical decision making to schedule a timely shutdown of the problem machine for corrective action. That means you see here, if whatever the problems are there with the machine can be immediately either replaced, can be repaired, or can be maintained properly for the specific time of that. So for evaluating of machine vibration, first we need to see that what exactly the desired level of the frequencies are there, and then you see here what exactly our amplitude which we can effectively control at that point, or whatever the amplitude which are being generating, we can say this is the usual form of the amplitude at the particular frequencies. So if we can measure these, you see like we can say the rotational speed of the machinery with this RPM part, and we can calculate you see the dedicated frequency which we are saying that you see these are the frequency which can come when any rotational features are there, the rotor, bearing, gear, shaft, whatever. So once we do that, certainly this allows the examination of vibration frequency in terms of the multiples of these rotational frequencies. And we can say the rotational speed is also, which is nothing but you see the fundamental frequency, and whatever the multiples are coming of these fundamental frequencies, we can say these are the higher harmonics or the super harmonic zones of that. Or even sometimes system is also exciting, say half of the natural frequency, 1/4 of the natural frequency, 1/8 of the natural frequency, 3/4 of the natural frequency. This is also harmonics of these like the natural frequency, but at the subharmonic system. So we can get you see here whether the system is absolutely exciting at the natural frequency, means the resonant condition, in the subharmonic region, superharmonic region, and then we discuss that you see how we can adopt the control strategy accordingly. So the vibration measurement is one of the specific and informative tool to adopt the corrective measures against that. The peak to peak distance which can be measured from the upper limit and lower limit is nothing but you see we can say like right from the microns level to any of the level, and it is clearly showing that how much total displacement is there of the rotating or you see the vibrating mass. And this is what the displacement, the velocity of vibrating object is continuously changing. The upper and lower limit of the object stops and reverse it in the we can say direction of the travel, simply providing its velocity at these 2 points, and then in between that you see here we can say what the variations are there of this velocity when it is approached to the zero, the upper and lower feature. So while passing through the natural or we can this neutral or the position of the rest, the velocity is at maximum. And since the velocity we know that like the nature of the velocity, and in continuous changing with respect to the time, the peak or maximum velocity is always measured, which gives the more important the informative feature, and it's commonly expressed in terms of like the millimeter per second or whatever it is at the peak part. And when we are trying to express the vibration characteristics in terms of velocity, both the displacement and the frequencies are being considered, because we as we discussed that the frequency is this velocity of any simple harmonic or the periodic vibration is absolutely depending on the amplitude, that what exactly the amplitude of these velocities are there, but also the frequency term linearly depending on both the parameters. And since the vibration object must reverse like a course of the actions at the peak displacement, this is always where you see where the maximum accelerations are occurring. So we need to consider right from you see the like we can say the displacement means the maximum amplitude and the frequency for the measurement of velocity in that. So like velocity acceleration is also continuously changing, and the peak acceleration is usually measured. So this is the third parameter of the dynamic system, in which you see here the out of 3, the 2 in which you see we are simply measuring the peak part, peak velocity and peak acceleration. So, displacement measurement can be importantly done, because especially in the lower frequency vibrations on the machine, which have you see like we can say the brittle components, these always you see like, because we know that the brittle components are harder and they are providing good damping part, the displacement must be measured, not the vibration, not the velocity and acceleration, because they can provide you rather we can say good kind of the accurate kind of the exciting part, the frequency part. And we can say that you see when we are talking about these brittle components, the stress that is applied is sufficiently like to step the component, and whatever the variations are there, that can be easily measured using this any of the displacement part, LVDT or something, the strain part or like that. So, many machines which have the cast iron frames or the cases, they are relatively brittle and are subjected to failure from the single large stress. So, acceleration measurement is also one of the important feature, because they are measuring the force part, that how much the inertial forces are there when the mass is rotating. And excessive force can lead to improper lubrication in various bearings or gear, and that is resulting in the failure. So, dynamic force which are being created by the vibration of due to any rotating member can be directly measured using the acceleration feature of that rotating mass, and you see we can find out that how much these inertial forces are being there, which can cause the failure part. So, generally a machine can withstand up to 8 times of the designed, we can say, static value before bearing failure occurs. So, we can say that we need to check it out, that this is general trend you see here. So, we can say that what exactly you see the kind of forces which are being generated during the rotational feature or any oscillating feature. And also you see it seems that sometimes whatever the small unbalances are there, they can also create the huge dynamic force, and even it is transmitted at the the faster way because of their robust connections, even at the overloading part of bearing or at gears or at the shaft part. So, ultimately we need to focus on that what exactly the international standard organizations are there, through which we need to find out the measurement, what are the the acceptable features are there for measurement of vibrations. So, for velocity we can say that, or for these the dynamic parameters, the RMS is one of the specific term or the unit which can be used directly, because based on these levels of these vibration in terms of RMS part, can at least find out you see that what is the level of this vibration is during this root mean square value of these part. So, when we are talking about velocity, then RMS tends to provide the energy contained in the vibration signal, whereas the velocity peak can correlate better with the intensity of vibration. So, this is what the things are. When we are talking about the root mean square trend of the velocity, then it is simply providing the energy, that how much energy is being contained in the velocity signal of the vibrating feature. But when we are talking about the peak to peak value, the maximum value, then you see we can rather see the intensity of these vibration in that. So, when we are talking about the higher velocity, that means the RMS is generally more damaging than a similar magnitude of this velocity at the peak level. So, again you see we can straightway go to the various the factors which are related to the waveform. So, the crest factor is there in that. The crest factor of waveform is nothing but the relation between the peak value of waveform to the RMS value, and sometimes we are saying that this is the peak to RMS ratio of the crest ratio. So, crest factor of the sine wave generally we are taking as 1.414 square root of 2, and the peak value is 1.414 times the RMS value is appropriate you see in such cases. So, crest factor is one of the important feature that can be used to train the machine condition straightaway, because it is relating the RMS and the peak value. So, when we are talking about these velocity, or when we are talking about the acceleration, we need to see that whether we are talking in terms of the just forces or the energy transformation. Because you see when we are talking about acceleration, which is nothing but the rate of change of velocity, It is simply referring to the spring mass body where the acceleration of mass is at maximum, like at the extreme limit of the travel, where velocity of mass is absolutely 0. So, how we can relate in terms of the energy or in terms of the forces together. So, first the significance of the dynamic parameters. So, the displacement, velocity or acceleration, which are, we are saying that these are the key parameters, needs to characterize, you see here, and in such a way that we just want to feature out the vibration, and we want to measure just to determine the severity of these vibrations, and these are often referred to the amplitude of that, because whatever the amplitude of these three quantities are there, they are generally saying that the amplitude of the vibrations. So, in terms of the operation of machine, the machine amplitude is the first indicator to indicate how good or bad the condition of machine is, or we can say that whatever the greater vibration amplitudes means the higher level of machinery defects are there. So, we can say that we can simply set the relationship between the acceleration, velocity and displacement with respect to, you see, the amplitude and the machinery health, which redefines the measurement and data analysis technique, like what exactly, you see, these details of these signals are, and based on that, you see here we can correlate that. So, if we are talking about, you see, the machine which is say exciting below 10 hertz, which can produce the, we can say, very little vibration in terms of acceleration, moderate vibration in terms of velocity and relatively large vibration in terms of displacement. So, displacement is used in this range, and in high frequency region acceleration value yield more significant than velocity or the displacement, because when we are talking about high frequency, if we are talking about displacement, we know that if it is a simple harmonic motion, x equals to a sin omega t. So, this displacement, which is clearly showing the amplitude and the sinusoidal feature, is just showing, you see, the frequency dependency in the sin omega t, whatever you see the, the sinusoidal features are there. But when we are talking about the velocity, this is clearly showing the amplitude and the linearly dependency on the frequency. So, a omega cos omega t is there, and when we are talking about the acceleration, it is absolutely minus a omega square sin omega t. That means, you see here, the acceleration is not only depending on the amplitude, but also, you see, the omega square. So, when we are talking about the high frequency zone or the ranges, acceleration is the only parameter which will clearly characterize in a correct manner about the vibration significance. So, you see here, when we are talking about the frequency over the range of 1 kilohertz, or we can say 60 kcpm, or even more than, you see, 1.5 kilohertz, the preferred measurement is absolutely the acceleration, and it is generally accepted that up to 10 hertz, or we can say, the 1000 hertz, the velocity is a clear indication, the good indication for severity of vibration, and above, we can say, this 1 kilohertz, the acceleration, and below 10 hertz, we can, whatever you see, the deforming features are there, or we can say, for, as we discussed about the this brittle material or the cast iron, when you see the low frequency excitations are there, the displacement is a good part, and that is why you see here, for controlling low frequency vibration, we are always adopting the spring. For controlling high frequency vibration, we are adopting the masses, and we just want to go to the resonant condition. Certainly, the damper is one of the key feature for controlling at that point of time to absorb the vibration excitation. So, in recent time, there is a simply concentrated effort to utilize the vibration monitoring in such a extended way that how we can just predict the vibration level based on what the sophisticated these the equipments are being available, and this is absolutely based on these sensors, whether we are using displacement, this velocity, or acceleration measurement devices. So, you see here, when we are talking about the model based diagnostic approach, which has the ability to combine the measurement signal with the vibration, we can say whatever the outputs, to make the real time the determinations of a rotor vibration or any kind of things, can simply gives the severity level, the alarming situation, and you see here what the comforting zones for health monitoring system. And when we are talking about the installation, means you see here where the vibration sensor to be installed, they are generally installed near the bearings, where you see the accelerometer or any these probes are being installed there, or else we can say that wherever you see like these kind of the rotating devices are there, whatever the closed by positions are there, we can install those things. But we know that like whatever this mid span locations between the bearings where the operator would most like to measure the vibration level, but cannot because you see the inaccessibility or the hostile environment for the vibration sensor, we need to see that what exactly the static means the housing positions are there where we can keep and we can get these vibrations, because these vibrations are transmitted as we discussed through this structural member, and because of this structural damping sometimes we are not able to correctly configure these inertial forces or whatever the dynamic forces which are being excited at the point of excitations. So, these model based approach for we can say like which is providing the virtual sensors are inaccessible for this rotor or the bearing locations to accurately say, you see if we have a defect at the bearing or some inner race or somewhere in cage, then it is starting like inducing the vibration, we cannot even put the gauge there itself. We need to put the gauge at some static position so that the vibration can be measured. But when the source of excitation and the measurement part, there is like the structural members are being connected, and as I told you, some material damping or the structural damping can be act against this kind of excitation, and it is really hard to find out the clear excitation feature at the source part. So, you see here when we are trying to measure the vibration using the sensors, we need to first we need to find first that what exactly you see the kind of like the vibration the signature which is being coming in those signature in these like we have the vibration capturing signals, and then you see here how we can like see that how many peaks are there in the vibration signature through which we can characterize the vibrations. So, digital measurement system which we are generally using but you see they are always more complicated structure than the analog ones, and the types of transducers which are being like using for like systems, sometimes we are using the vibroacoustic like you see the microphones to measure the sound pressure, accelerometer to measure the acceleration of the solid structure, or the force transducer to measure the forces in the solid, which are being generally used and coupled with that. And the principle behind force transducer are not to describe, but mainly you see here to see that how you see the forces are being there in like a generated, because even we can get those inertial forces through the accelerometer also. So, this is what it is. We can see that in which you see like these wherever you see the positions are there, we can put these like the microphones or the accelerometer. This is what my main transducers, and through that I can get you see these signals. Or even you see when we have such kind of things with this like the digital filtering, we can get you see like the frequency peak, the FFT. So, this is my time domain, this is my the frequency domain, and it can clearly give that what kind of you see the exciting frequencies. Again, we can get the responses in the two main domains, as we discussed already in our initial lectures. The time domain is clearly giving the variation of the vibration amplitude in terms of the displacement, velocity and acceleration. The FFT, which is nothing but you see we are using the key information of the time domain part, and we are trying to convert this in the stationary waveform from time domain to frequency domain using the Fourier transformation. And that is why frequency domain information is simply used to say that fast Fourier transformation, discrete Fourier transformation, short STFT also, short term Fourier transformation, anything which is being required. Sometimes STFT is being used for like if any additional peak is there because of some abrupt changes, and the transient feature is coming which is not the stationary part, we can use either the wavelet or any kind of signal processing unit for these like to feature out the non-stationary form of this signal part. So, like we can characterize these various the signal processing part, but the one of the like the important characteristic which are being commonly used for all the type of transducers are first the sensitivity. The sensitivity is simply indicating the ratio of electrical output to mechanical input. Second is the frequency band, that what exactly you see the upper and lower frequency limits are there, so that we can simply put that this is what you see my transducer sensitivity, which is varies you see right from like within this part. So, this is what my tolerance range is there for that, and octave bands are there for like we can say this the third octave band and all. The dynamic range, which is simply indicating the lower end this upper limit of the amplitude in between the transducer sensitivity varies within the given tolerance range, and the dynamic range is commonly like being there in the decibel sound, the decibel part with respect to the reference value. So, the lower dynamic boundary is simply like determining by transducer's electric noise, and the upper this like we can say dynamic boundary of the transducers when it is being loaded beyond the mechanical linear regions that can be get. So, the first part is coming, which is the accelerometers. Accelerometers nowadays is one of the like the fascinating device which is based on mainly, as we discussed, the piezoelectric base. So, when we are talking about the accelerometer, the system damping is almost like having the negligible effect. Thus, for we can say that we can simply use these like the accelerometers, which is based on you see the piezoelectric level having the equation of motion m, say this one m neta double dot plus c v neta dot plus k neta equals to minus m y object. This equation is simply like a forming of that one. We have the object where the vibrations are there, and this has you see the like the displacement of this y, and you see this accelerometer which is being putting on that one you see here. So, we have the y base. Y base is nothing but the displacement of the base which is being now like sensed by this accelerometer, and in this you see here this accelerometer is also moving along with our base, and in that accelerometer we have the stiffness k, Cv which is nothing but the damping, and the mass which is being there in the accelerometer has you see like the movement is the neta. So, that is why previously which I shown you see was m neta dot, that is you see the inertial force within the accelerometer device, and then Cv the this damping and restoring forces of the our accelerometers are. So, when we are trying to make the balance of this say neta, which is nothing but equals to y minus y object, when we are trying to make the force balance conditions, we have you see my double dot equals to m into you see neta double dot and y plus y object double dot, that is what you see the total overall impact of this part into you see which is making balance of m into acceleration. So, accelerometer load cell is usually you see like having a piezoelectric crystals, and like they are simply registering a compressive load which is necessary, we can say preload kind of spring to keep it in compressive part. So, we have you see the spring and the damper on which you see we have the mass which is always keeping in the compressive or the preloading feature, and the piezoelectric crystal which has like inherent you see the inherently property with the quite stiff part in comparison to the other preload spring. So, we can say that the load cell essentially register all the dynamic forces required to accelerate the inertial the internal masses towards that. So, this is what you see like as we already discussed about the piezoelectric features and how you see the PZT this piezoelectric based accelerometers are being used effectively to measure the accelerometer in that. The second part is in this is velocity transducers. So, velocity pickups are very popular transducers, or we can say like for monitoring the vibration of any rotating machinery, because we know that it can be straight installed on the machine easily, and you see it's a very low costing as compared to the accelerometers. So, for these two reasons we can say that generally we are using you see like the velocity probe straightway, and we can keep like just we can use as a vibration transducer and straightway keep on the rotating machinery for even for longer time, and can be utilized for variety of these like the configurated machines. So, in that when a coil of wire is being moved through the magnetic field, a voltage is induced across the end of like across these like the end of the wires of the coil, and this induced voltage is caused by you see like the transferring of the energy from fixed flux this whatever the flux filed like just like to the magnet to the wire coil. So, whatever the flux which is being like just we can say flux fields are there exactly at the this magnet point, they are being like they are right from to this point to the like the coil this coiled wire, and as the coil is forced through the magnetic field by any vibrating or any kind of the injecting motion, a voltage signal which is representing the vibration like the produced vibration is being transmitted, and this velocity pickup is nothing but the self generating sensor required in no other any external device, and it is being transmitted there itself. So, you see here the corresponding vibration signal can be generated, as you can see in this diagram, that here we have this spring, and whenever it is being coming, it is being straightway go to the wire coiled. So, in that wire coiled, you see here whatever the things are being coming, straightway it will pick up and then it is being transmitted through this. So, you see here, and in all along that you see we have the damper, and this coil which is there in between the magnets is immediately you see sense that, and then it is being transmitted through these like whatever the damper and the spring devices, and then we can measure that. So, this is you see like one of the important we can say vibration pickups are there using this velocity pickup, this velocity we can say probes. So, velocity sensors are always you see like we can say susceptible to across the vibration features. Even in that you see here, whenever we are trying to see that if the higher output sensitivity is there, where like the electric noise is creating the useful is creating the use problem, these pickups are always being useful. So, for larger signal and for like whatever the vibration level is quite high as compared to this noise level, the velocity pickups have like the different frequency responses, which are absolutely depending on you see that what exactly the sensitivity level is given in these velocity probes. But most of the peaks like these most of the pickups of these velocity probes, they can be easily worked within the this frequency response range, right, from 10 hertz to as I told you the 1 kilohertz. But nowadays you see here we have right from uniaxial, biaxial and even triaxial accelerometers are there, and you see even these accelerometers which are absolutely based on these piezoelectric base, they are absolutely even sensitive, and they can provide, because they are the calibrated one, and they are providing absolutely like the accurate information in any of the axes with you see whatever the this PZT acceleration features are. So, you see like the pickup frequency response, when we are talking about the velocity probe, then you see like we can get straightway from the velocity pickups within the like we can say expected vibration frequency of the machine. And we know that the velocity transducer, which has the like the internal moving part, and like that cannot be given accurate reading in any hostile environment, because we know that when the these movements are there, certainly you see here this hostile environment or like some kind of use amplitude is creating the problems within that, and that is why you see here the, as I told you, the accelerometers are the perfect one for measuring this. If you are talking about the displacement transducers, we know that there are a variety of the displacement these probes are being there, in which we have the fixed and movable part, and we know that the movable part is absolutely attached to these we can say the break this entire unit with the breaker part, and when it is moving with the contacts, we know that like the fixed part is absolutely acting as a reference, and we can get to see what the differences are there. So, you can see this one, we have the fixed part and the movable, and they are being rested on that. So, whatever the movements are there, you see under the load conditions, we can see the differences and we can get the displacement or this one. And even you see here we can get the deformation with the using of strain gauges, LVDTs and all. Through that you see we can find out you see what exactly you see like the strain features are there towards that. The last part in this chapter is the calibration. The calibration of transducer for accurate measurement system is one of the essential feature, because we just want to maintain the high standard of the measurement quality. The transducers which are absolutely you see like first calibrated, and second part is the traceability. So, you see here like we can say when the things are being working, we need to check it out that whether like the instrument which should be like first the calibrated should be there, and then you see here we need to trace that what actually the problems are. So, in practices we are always going with the regular calibrations of the equipment, and we need to find out that you see here like we need to just put that you see what exactly the calibrated measurement values are there, and in this you see here we can go with the two main phases. One, the calibration based on the transducer's sensitivity. in which we need to see that whether the calibrator is absolutely there within the given sensitivity level or not. And the knowledge of the amplification of the rest of the measurement system is like one of the important feature. And second is the entire measurement chain is calibrated simultaneously, and the transducer is subjected to the known vibration or the sound signal, and then the system output can be checked that whether we are getting the correct value, the desired value or not, and otherwise you see here whatever the corrective measures are being taken. So, this is the most common and convenient method which we are always being using for calibrating the instrument prior to go for the measurement feature. So, you see this is one thing, we know the standard value, and then you see here when we are exciting or when we are giving the sound value. So, say in the first part if it is 120 dB or 250 hertz, when we are just putting, if we can calibrate using the sound level meter of 124 dB, or if we can calculate, if we can measure using this like the frequency part 250 hertz, this is absolutely okay. If it is not, then you see we need to check it out that what exactly you see like the other features are there through which we can calibrate. So, one is the standard one or the known value, one is you see where we need to calibrate, we can check the output of that, and we can check the error of this. Lastly, even to calibrate the vibration measurement in nowadays, you see here they are absolutely like we are using the portable battery driven electrodynamic vibrators through which we can excite at the known frequency and amplitude, and we can see that whether we are measuring through these accelerometers or velocity probe or anything you see of the same level of frequency or the amplitude or not. If any error is there, we need to make a proper corrective measures in that. So, we can calibrate through this way. So, there are lots of you see calibration devices are there, and we can prior to go for measurement we can check. So, in this lecture we mainly discussed about that you see what the basics of the vibration measurements, what is the need of the vibration measurement, because you see here the control strategy can be adopted, but prior to that we need to know the values, we need to know the vibration features of the entire structure is. And once you can feature out, once you can characterize the vibration, then it is very easy to adopt the proper corrective measure to control the vibrations. And for that, as we discussed, there are three main devices. One is the accelerometer, second is the velocity probe or the displacement probe can be adopted accordingly. So, in the next lecture we are going to discuss about these, you see that how in the measurement technique how we can go for how we can feature out these vibration signals, and then how we can characterize those things. Thank you.